cooler shafts here. In the sixth topic, okay, we discuss about the shafts here. In the seventh topic, we'll discuss about the columns here. That means in the strength of the material, we design the four members. The first one bar, second one beam, third one shaft, and fourth one is the column. But one thing you have to remember, to design the any member in the strength of the material, we are going to follow the four criteria here. What are those four criteria? One is the strength criteria, the second one is the stiffness criteria, third one is the strain energy criteria, and fourth one is the stability criteria here. To design the any member, is it a bar, beam, shaft, frame, any kind of member, we have to follow these four criteria here. And you can look at that four criteria here: the strength criteria, stiffness, and strain energy criteria, and stability criteria. What is meant by the strength criteria? Okay, the strength criteria says that the stress induced in the member is always less than the strength of the material, then the member is safe, otherwise it is failure. Is it audible? Are you follow? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Could you understand?
Yes, sir.
Hello, sir.
Yes, yes.
Yes,
Please
sir.
tell me.
Sir,
Okay. Tell me.
sir, one person join అవుతారంట ఒకసారి చూడరా సార్.
Yes, I'm not audible. Once again. Hello?
Some students are outbox, sir. Please join.
Sir, we can. Sir, Sunny, sir. Hello?
Some people are asking to join, sir.
I am not joined here, or your faculty is there. He is admin.
Okay, sir.
You can ask them. First, are you follow this?
Yes, sir.
Okay. If you have any doubt, you can ask, no problem, after completing the class. Okay? Once again,
Okay, sir.
please write down the notes also, no problem. First one, to design the any member, is it a bar, beam, shaft, frame, any member, we have to consider in the four criteria here. The first one is the strength criteria. The strength criteria says the stress induced in the member is always less than the strength of the material, then the member is safe. But we may get a one doubt here. Sir, how to compare stress with the strength here? First, we will discuss about the strength here. The strength means it is the ability of the material to resist the external load. Without failure is called as a strength here. The strength can be found by doing the experiments. I think in our college laboratory, MOS laboratory, there is a different kinds of tests are there. There is a tensile test is there, and compressive test is there, and shear test is there here. These tests, to find out the strength of the material by using the UTM mission, we can find out the tensile strength here. By using the compression testing mission, we can find out the compressive strength here. By using the shear testing mission, we can find out the shear strength here. But one thing you remember, there is no other kind of strengths here. Only there is a three kinds of strengths. One is the tensile strength, second one is the compressive strength, and third one is the shear strength here. Okay. Now, if you take the one material, any kind of material, if it is a ductile material or brittle material, we know the example for ductile material is mild steel. The example for brittle material is concrete or cast iron. These are the examples for brittle material. For any kind of material, there is a three kinds of strengths. One is the tensile strength, second one is the compressive strength, and third one is the shear strength here. Now, if you are using the ductile material, for ductile material has high tensile strength here, and low compressive strength here, and low shear strength here, and medium compressive strength here. That means, suppose for example, if you are using the one member, in that member the maximum tensile stresses will be developed here. In such a case, we can use the ductile material, because ductile materials are very strong in the tension. Suppose for example, if you are using the brittle material where the tensile stresses are developed more, in such a case, no doubt in that all that member is failure. Okay, that's why while selecting the material, it is very useful sentence. The ductile materials are very strong in the tension, weak in the shear, and moderate in the compression. Whereas in the brittle materials are very strong in the compression and weak in the tension and moderate in the shear. Okay, these are the two beautiful sentences in the strength of the material here. But we may get a one doubt here. Sir, is there any other strength? Okay, is there any other strengths here? No, there is only three strengths. One is the tensile, second one is the compressive, and third one is the shear. But we may get one more doubt. Sir, while comparing the stress here, okay, how many kinds of stresses are there? One thing you have to remember, we are calling as a different names. What are the stresses here? Sometimes we are calling as a axial stresses. Sometimes we are calling as a compressive stresses. Sometimes we are calling as a tensile stresses. Sometimes we are calling as a bending stresses and shear stresses and longitudinal stresses and bearing stresses, and there is a different kinds of stresses are there. But we may get a one doubt. Sir, the bending stress is induced here in the member. In such a case, how to compare with the strength here? What kind of strength we are considering? That actually there is a three kinds of strengths here. One is the tensile, second one is the compressive, and third one is the shear. Okay, but one thing you remember, the stresses are ultimately three. One is the tensile stress, second one is the compressive stress, and third one is the shear stress only. There is no other stresses. Because of our convenience, sake of convenience, we are calling this a different names. Bending stress. Bending stress means it may be the tensile or compressive. Suppose let us consider the one simply supported beam. Okay, when the simply supported beam is subjected to some external load, we know that the top fibers are subjected to the compression and bottom fibers are subjected to the tension. In the top fibers, there is a compressive stresses will be developed here. In the bottom fibers, there is a tensile stresses developed here. This compressive and tensile stresses, both are we are considering as a bending stresses. That means the bending stress, it may be the tensile or compressive. Okay, after calculating the bending stress, we can identify whether the stress is the tensile stress or compressive. Suppose, for example, in the bottom fibers, the tensile stresses will be developed. So, that value compare with the tensile strength of the material. If, suppose, for example, the tensile stress value is 250 megapascals. For a particular material, the tensile strength is 300 megapascals. Then here 250 should be less than the 300. That means the member is safe. Okay, suppose for example the tensile stress is 350 megapascals, but the tensile strength of the material is 300, then the strength is greater than the the stress is greater than the strength here, then we can say that it is failure. That is the meaning of strength criteria. Okay, that's why always in the strength of the material we can calculate the stress. The stress is the very important parameter. Okay, that's why we can calculate the stress here. Okay, very important parameter. Like in the engineering mechanics, the force is the very important parameter. Like in the strength of the material, okay, the stress is the very important parameter. Actually, our subject is strength of the material, but we never calculate the strength here because the strength cannot be found theoretically. That means we are not using the different formulas, so we can't calculate the strength here. The strength can be found by doing the experiments only. Okay, what kind of experiments? Okay, there is a UTM machine is there to calculate the tensile strength, and compression testing machine is there to calculate the compressive strength, and shear testing machine is there to calculate the shear strength here. Okay, could understand or not, students? Hello?
Yes, sir.
Yes,
Hello?
sir.
Could understand the strength criteria?
Sir.
Yes, sir.
If you have any doubts,
No, sir.
okay.
No, sir.
Finally, I conclude the strength criteria says the stress is always less than the strength of the material. The stress can be found, the stress can calculated by using the formulas. Okay, sigma is equal to P by A. By using that formula, we can calculate the stress. And the next one, bending stress, F is equal to M by Z. By using the M by Z also, we can calculate the bending stress. And the shear stress, tau is equal to F divided by A. By using that one, we can calculate the shear stress. So, in the strength of the material, we can calculate the stress by using the various formulas. but the strength can be found by doing the experiments. After that, we can compare these two. If the stress is less than the strength of the material, then the member is safe. Otherwise, it is failure. That is the first criteria, which is called as a strength criteria. Okay. The next one, but we may get a one doubt. Sir, okay, why should you use the sigma is equal to P by A? Always can use the sigma is equal to P by A. Please remember, we can use the stress formula. Which formula we can use? That is depends upon the member. Suppose, for example, the member is bar. Do you know what is meant by the bar? The bar is a member which is subjected to axial load. That is called as a bar. Okay, the next one is the beam here. Beam is nothing but it is the member which is subjected to the transverse load here. The shaft is a member which is subjected to the twisting moment here. Like that, first we can identify the member. Okay, what kind of member we can design? If we are using the bar here, we can use the sigma is equal to P by A. If we are using the beam here to calculate the stress, F is equal to M by Z. If we are using the shaft here, we know that one equation, torsion equation, T by J is equal to tau by R is equal to G theta divided by L. Okay, by using that expression, we can calculate the shear stress here, where tau gives the shear stress. Okay, that is the strength criteria, first one. The next one, stiffness criteria. Okay, please remember, in the stiffness criteria, always we can calculate the deformation. Okay, we know that deformation we are calling as a different names here. Sometimes we are calling as a elongation, sometimes we are calling as a contraction, sometimes we are calling as a deflection, sometimes we are calling as a angle of twist, sometimes we are calling as a buckling here. We are calling as a different names. Okay, that names, that is depends upon the name of the member. If it is a bar, we are calling as elongation or contraction. If it is a beam, we are calling as a deflection. If it is a shaft, we are calling as an angle of twist here. Okay, so we may get a one more doubt. Sir, how to calculate this deformation? If it is a bar, there is a one formula, delta is equal to PL by AE. If it is a beam here, deflection y is equal to some WL cube divided by 3i. If it is a shaft here, theta is equal to TL divided by GJ. By using those equations, we can calculate the deformation. Okay, and that deformation, compare with the permissible deformation. Suppose, for example, we can design the one member. That member can permit some amount of deformation. Okay, but if you are applying the load on that, if the deformation produced in the member due to the textural load is more than the permissible deformation, that member is failure. That criteria is called as the stiffness criteria. Could you understand?
Yes, sir.
Hello? Could you understand?
Yes,
Can I
sir.
explain once
Yes,
more?
sir. Yes, sir.
Could you understand stiffness criteria? Hello?
Sir, myself Sunny, sir.
Sir.
Sir, I have a small request, sir.
No problem.
Sir, may you turn on your phone to portable mode, sir.
Sir.
Landscape mode, sir.
Okay, sir. 1 minute.
The screen will be here, sir.
Sir, they can zoom, sir. No problem. The students can do zoom also. No problem. 1 minute. Okay, sir.
Okay, sir. Now it is clear, sir.
The students also can zoom, sir. No problem. Sir, actually, this is the introduction of the strength of the material. We can't write the each and every matter in that. First, please understand these 4 criteria are very, very important, sir.
Okay.
The stiffness criteria. Once again, I repeat the stiffness criteria. The deformation produced due to the external load is always less than the permissible deformation. Then the member is safe. Otherwise, it is failure. Okay, that is the stiffness criteria. How to find out the deformation due to the external load? That is depends upon the member. If it is a bar, we are using the one formula. If it is a beam, we are using the another formula. If it is a shaft, we are using the another formula. That's why what I said previously, first we can identify the member, whether it is a bar or beam or shaft. Okay, that criteria is called as a stiffness criteria here. The next one is strain energy criteria. The strain energy criteria means every member can store the some amount of energy. Suppose, for example, there is a one spring is there. If you are applying the some external load, the spring can store the some energy. That energy is called as a strain energy. Suppose, for example, if you remove that load, the energy can disappear. That's why the strain energy can store it in the elastic members only. It cannot store it in the plastic bodies here. It can be stored in the elastic bodies only. That strain energy stored in the elastic member due to the external load is always less than the permissible strain energy. Then the member is safe here, otherwise it is failure here. That is called as a third criteria, that is called as a strain energy criteria here. Once again I repeat here, strain energy due to the external load, strain energy stored due to the external load is always less than the permissible strain energy. Suppose we can design the one spring. The spring can store the 300 kilojoules of energy. Let us assume that 300 kilojoules of energy. Suppose if you are applying the load on that spring here, if you store the 200 kilojoules of energy, that 200 kilojoules is less than the 300 kilojoules because that spring can carry the maximum that can store the maximum 300 kilojoules here. But here, how much kilojoules of energy it can store due to the external load? 200. That 200 is less than the 300. That's why, that member is safe here. Suppose if you are applying the another load, due to that load here, the strain energy stored in that one is 350 kilojoules. That 350 kilojoules is greater than the 300 kilojoules. No doubt in that all, that member is failure. But one more thing you have to remember, failure means, don't think like that it can break into the two pieces. Failure means it is not functioning. We can design the one member for a particular purpose here. It cannot satisfy, then it is called as a failure. Suppose, for example, we can design the beam here to carry the transverse load here. The beam cannot carry the transverse load, then it is called as a failure. Don't think like that. Failure means it can break into the two pieces. That is called as a strain energy criteria. And fourth one, it is called as a stability criteria here. The stability means, suppose if you are applying the some load on that, just it can deflect or deform. Now if you remove the load, it will get the original position, then that member is stable. If it does not regain the original position, then it is in the unstable condition. So that criteria, always the member should be stable. That means when you remove the load here, it comes to the original position, then it is called as a stable. If it does not come to the original position, then it is called as in an unstable condition here. Always the member should be in the stable condition. Generally, the stability criteria we are considering in the columns here. Because we may get a one doubt here. Sir, while designing the bar, or beam or shaft, we are not considering the stable criteria here. But why should you considering the stable criteria in the columns here? Because the column is a slender member. If the length of the column is increases, length means height of the column is increases here, no doubt in that all, if the height is increases, those members goes to the unstable condition here. Finally I conclude, when the member should be in the stable, the center of gravity of that member is below the ground, very nearer to the ground. Then those members are in stable here. The center of gravity of the member is far away from the ground, then it is in the unstable conditions here. Generally the columns are very slender members which are placed vertically. That means the center of gravity is also far away from the ground. That's why first we can check it with the stability criteria. Is it in the stable? Then we can check it remaining three criteria here, because it is very weak in the stable, because it is a very slender member here. The remaining any member, no need to consider in the stability criteria, just we can consider the three criteria. One is the strength criteria, second one is the stiffness, and third one is the strain energy. These are the four criteria we are considering to design the member. Very, very important here. That's why in the strength of the material, the predominant terms, one is the stress, second one is the deformation, third one is the strain energy. To design the any member, we are to considering these things here, stress and deformation, and and next one is what is the third one? Strain energy. This is that's why to design the member, following criteria are considered. That is the next slide. Next slide. What is the definition of the stress? Generally, the student says that the stress is equal to load by area. Okay. Don't think like that. If you are applying the load, the stress will be produced here. Suppose, for example, I am placing the one member, okay, on the ground here. If you are applying the load on that, then what happens here? Some work will be done. There is no stresses. Some work will be done because we know work done means force into displacement. Okay, we are applying the some amount of force, and also the member gets some amount of displacement here. That force multiply with the displacement, which gives the work done. Don't think like that. If you are applying the load on the member, the stresses will be developed here. When the stresses will be developed here, if you are applying the load, that load can resist the member. Okay, then the stresses will be developed here. The stress means internal resisting force per unit area is called as a stress here. Internal resisting force. That's why we can look at that slide here. When a material is subjected to the external force, a resisting force is set up within the component. Okay. Okay. Otherwise, the stresses will not be developed here. Suppose I am placing the one member on the ground. If you are applying the force on that, then the member can move from one place to another place. That means it will get the some amount of displacement. Due to that displacement, the stresses will be developed? No. Okay, to develop the stresses here, due to the external load, the internal resisting forces will be set up. Then the stresses will be developed here. Suppose, for example, if you pull my hand, this is the one example. If you pull my hand, I am moving with you. There is no stresses in my hand here. Suppose, for example, I can resist the load, then the stresses will be developed in my hand. That is called as a stress here. Stress means our in the body. Okay, the stress means pain. Okay, that's why we can look at the second sentence. The internal resisting force per unit area acting on the material is called as a stress at a point. Is called as a stress at a point here. Okay, please remember the stress means internal resisting force per unit area. When you go to the interviews, don't say that simply load per unit area. Okay, internal resisting force per unit area. Okay, and we may get one more doubt. Sir, while doing the problems, okay, but in any textbooks, always we can look at this one, internal resisting force per unit area is called as a stress here. But while doing the problems here, we are using the any kind of textbooks. Okay, is it Indian authors or foreign authors here? Always we are using the load per unit area. Why should we are using the load per unit area? But why we are not using the internal resisting force means? But one thing you remember, okay, it is strictly speaking, okay, the definition of the stress is internal resisting force per unit area. But sometimes we are using the load per unit area also. When we are using the load per unit area, while designing the member up to elastic limit, then we are using the load per unit area or internal resisting force per unit area because the load is equal to internal resisting force. But beyond the elastic limit, the internal resisting forces are always less than the external loads. That's why we get the permanent deformation. Yes. But within the elastic limit or up to elastic limit, if you are applying the 50 kilonewtons of load, the internal resisting force will also 50 kilonewtons. Internal resisting force means always opposite to the external load. Suppose, for example, if you put the 50 kgs weight on my head, if I can resist the 50 kg, okay, that 50 kg is called as internal resisting force and external load. But if you put the 60 kg weight on my head, but I can't resist that one. That's why my resisting for maximum resisting force is called as maximum resisting force is 50. That's why I can't resist the 60 kg weight. That's why, okay, always, okay, we can use the internal resisting force per unit area to define the stress here, but load per unit area you can use the when you design the member up to elastic limit. Okay. Hello, students. Hello.
Okay, sir.
Understand what is the difference between the internal resisting force and external load? Okay. Load means we are applying the different kinds of forces externally. That is called as a load. Due to that external load, the internal resisting forces which is developed in the body. Every body has some internal resisting force. Every body has some internal resisting force. That internal resisting force is equal to the external load up to elastic limit. That internal resisting force, less than the external load in the plastic limit here or plastic region. But we may get a doubt here, sir. What is meant by the internal resisting force? We can look at the next slide here. Okay, now I am applying the tensile force on the member. Okay, now we can look at here. There is a arrowheads which is represented by a red color. Those are called as a internal resisting forces. Internal resisting forces are always opposite to the external loads. Okay, but in the BTech level, up to BTech level, okay, always we can design the member up to elastic limit. That's why we are calling as a external load. Sorry, we are calling as a external load or calling as an internal resisting force. Both are same. But when you go to the interviews, okay, don't call as a stress is equal to load by area. Please call as a internal resisting force per unit area. Okay, that is the meaning of internal resisting force here. Okay, now we are using the formula stress is sigma is equal to force per cross sectional area or unit area, no problem here. Okay, this is the formula we are using to calculate the stress, not any kind of stress here. This formula used for to calculate the normal stress. Normal stress means it may be the tensile or compressive. If we are calculate the bending stress here, we are using the F is equal to m by z. If you want to calculate the shear stress in the shafts here, tau is equal to T divided by ZP. That kind of formulas we are using to calculate the stress. But already I told that why should we calculate the stress here? After calculating the stress, okay, that value compare with the strength of the material. If the strength is more than the stress here, then the member is safe. Otherwise, it is failure. Okay, and next one, very important point here. This is the very important, I think, which are not available in any local standard textbooks like a RS Kurmi or Ramamrutam or that kind of Indian standard textbooks. It is not available. This concept here, stress at a point. Very, very important concept here. This is also very useful concept for GATE. Okay. Now, stress at a point. First, before going to study about the any physical quantity. Now, physical quantity means there is a number of physical quantities are there, such as displacement is the one kind of physical quantity. Velocity is the physical quantity. Mass is a physical quantity. Weight is a physical quantity. Okay, these are called as a physical quantities. Like stress is also a one kind of physical quantity. Okay, but we know any physical quantity, it can be categorized as a okay, those physical quantities are scalar quantities or vector quantities. We know that scalar quantities means it is only depends on magnitude. Vector quantities means depends on both magnitude and direction. Okay, suppose for example, scalar quantities means mass is a scalar quantity, and the next one, weight is a scalar quantity. Speed is a scalar quantity, distance is a scalar quantity, and one more very important one which are very useful in the fluid mechanics, pressure is also a scalar quantity. Pressure is also a scalar quantity. Okay, we know these quantities, scalar quantities, are independent on direction. Okay, it is independent on direction. That means any direction which gives the same magnitude. Magnitude means value, which gives the same magnitude. Those are called as a scalar quantities. And vector quantities means it is depends upon the both magnitude and direction. Okay, both magnitude and direction. That means we know displacement, velocity, acceleration, force, this kind of quantities, vector quantities here. But we may get a one doubt. Sir, stress is a scalar quantity or vector quantity? But one thing you remember, stress is not a scalar or vector quantity. It is a tensor quantity. T-E-N-S-O-R, tensor quantity. Tensor. What is meant by the tensor quantity? It is not only depends upon the magnitude and direction, it is also depends upon the plane. Yes, it is also depends upon the plane here. If you look at that slide, I am considering the three-dimensional body. Okay, in that three-dimensional body, there is a x direction, y direction, and z direction is there. Okay, the plane which is perpendicular to the x direction, I am calling as a x plane. The plane which is perpendicular to the y direction, I am calling as a y plane. The plane which is perpendicular to the z direction, it is called as a z plane. That means now we have how many planes here? 3 planes. X planes, y planes and z planes here. There is a 3 planes are there. Okay. There is a 3 planes are there. Okay. Now, what I said here, stress is a tensor quantity. Not only the stress, strain is also a tensor quantity. And in the engineering mechanics, we studied about the moment of inertia. Moment of inertia is also a tensor quantity. Okay. Angular velocity, it is also a tensor quantity. We know that angular velocity, we are using the angular velocity formula so many places here. That is also a tensor quantity. And Young's modulus is also a tensor quantity. Poisson's ratio, tensor quantity. Okay, shear modulus, bulk modulus, these are all called as a tensor quantities here. That is a very important point here. Okay, but except two. One is the moment of inertia and angular velocity. These two are, sometimes it is a tensor quantity, sometimes it is called as a scalar quantities here. Suppose, for example, let us consider the one fan. The fan is rotating with some angular velocity or not? It is rotating with some angular velocity, but that fan is rotating with some fixed axis. Okay, the member which is rotating with a fixed axis, okay, that member has some angular velocity. In such a case, that angular velocity is called as a scalar quantity. That means, okay, the member is rotating with some fixed axis, then it is called as a scalar quantity. It is rotating with some angular variable axis, then it is called as a tensor quantity. For example, let us consider the one bicycle wheel. The bicycle wheel is also rotating with some angular velocity, but is it a fixed axis? No. Okay, it has their own axis. Okay, at different times it has a different axis here. Okay, there is no fixed axis for bicycle wheel or a motorcycle wheel or any heavy duty vehicles here. We can look at here the axis, it can changes. In such a case, it has some angular velocity. That angular velocity we are calling as a tensor quantity, like a moment of inertia also like that. Okay, if the member it can rotate with a fixed axis, then it is called as a scalar. It can rotate with a variable axis, then it is called as a tensor. But the stress, strain, and elastic constants or Poisson's ratio, these are always tensor quantities here. Okay, tensor means it is depends upon plane, direction, and magnitude. Yes, plane, direction, and magnitude. But one more thing you have to remember, very simple to identify, is a scalar, vector, or tensor. One thing you have to remember, for scalar quantities, there is no subscripts. Suppose, for example, displacement, okay, which is represented by the some S. Yes, there is no subscripts here. Suppose, for example, velocity, okay, we can call as a Vx, Vy, and Vz. But whereas in the fluid mechanics are like that, here U, Vw. U means velocity in x direction, V means velocity in y direction, W means velocity in z direction. Okay, that's why some textbooks Vx, Vy, if one subscript is there, then it is called as a vector quantity. If there is a two subscripts, okay, then it is called as a tensor quantity here. If you look at this figure, okay, there is a tau xy is there in the figure, and tau xz is there, tau zy is there, zx is there, and tau yz is there, tau yx is there. That means there is a two subscripts. Actually, for sigma also, sigma xx, okay, sigma yy, sigma zz. Okay, simply it is in the figure, simply it is represented by the one sigma, one x here. Don't call as a 1x here, sigma xx. Okay, in this figure, the first subscript represents the plane. The second subscript represents the direction. Suppose, for example, tau xy is there. What does it mean? Okay, the shear stress on x plane in y direction. What I said, the first subscript represents the plane here, and the second subscript represents the direction. Okay, second subscript represents the direction here. We can look at the any one. Suppose, for example, tau yz is there. That means shear stress on y plane in z direction. Okay, like that. So to represent the stress, Okay, we may ask the one question, sir, the stress is developed on which plane in which direction? That is the very important. Suppose simply I am calling as the stress value is equal to 50 megapascals, but immediately we may get a doubt here. These 50 megapascals are developed in a which plane in which direction? Otherwise, there is no meaning. Okay, simply I am calling as a 50 megapascals. We can't, okay, answer for that question in which plane, in which direction. That means it is a meaningless. Okay, so that kind of quantities we are calling as a tensor quantity. The stress is a tensor quantity. It is depends upon the plane and direction. And we can observe this figure. Okay, sigma x, sigma y, sigma z. You can look at these three. These stresses are always perpendicular to the plane. Right or wrong? These three are always perpendicular to the plane here. Okay, sigma x is perpendicular to the x plane, sigma y is perpendicular to the y plane, sigma z is perpendicular to the z plane here. The stresses which are induced perpendicular or normal to the plane is called as a normal stresses. Is called as a normal stresses here. Okay, that kind of stresses. Please remember the normal stress is always represented by sigma. Okay, that's why sigma xx, sigma yy and sigma zz. Sigma xx, but in the figure only one subscript is there. Actually sigma xx, the first subscript represents the x plane, second subscript represents the x direction. That means the normal stress on x plane in x direction. Okay, now we can observe here, this is a three-dimensional body. Okay, now on each plane, how many directions are there? Three directions are there. That means on each plane, three stresses are there. Okay, one is the normal stress, but we may get a one doubt. Sir, what is the remaining two? Okay, we can observe that figure. Remaining two, is it parallel or tangential to the plane or not? Okay, is it parallel or tangential to the plane? Please remember the stresses which are induced parallel or tangential to the plane is called as a shear stresses. The shear stresses is represented by the tau. Okay, so on the member there is a two kinds of stresses will be developed here. One is the normal stresses, second one is the shear stresses. The normal stresses are always perpendicular or normal to the plane. The shear stresses are always parallel or tangential to the plane. Tangential to the plane here. Okay, so on each plane, how many stresses will be developed here? Three. Okay, two shear stresses and one normal stress here. On y plane also three, two shear and one normal. On z plane also three, one normal and two shear here. Then to define the stress at a point. Okay, yes, to define the stress at a point, the 9 stress components are required. Okay, 3 normal stresses and 6 shear stresses. You can look at this slide here. Okay, now those those 9 stress components I can put into the matrix. Sigma xx, tau xy and tau xz like this here. These 9 stress components are required to define the stress at a point here in a 3-dimensional state. Okay, now we can look at tau xy is equal to tau yx and tau yz is equal to tau zy and tau zx is equal to tau xz. Okay, but sir, why it tau xy is equal to tau yx here? Because this is called as a complementary shear. Okay, we will discuss later also that one here. Okay, there is a one derivation is also there. Okay, how to equate the tau xy is equal to tau yx here. Please remember tau xy is equal to tau yx here. Actually, generally we are calling like this here. Tau ij is equal to tau ji due to the complementary shear. Okay, due to the complementary shear. That's why to define the stress at a point, how many independent stress components are required is 6 only. Total components are 9 here, stress components to define the stress at a point. But independent, that means to calculate the tau xy, no need to calculate the yx. If we calculate the tau yz, no need to calculate the zy here. Okay, that means independent stress components are required is 6 here, 3 normal stresses and 3 shear stresses here. Okay, and one more thing you have to remember, stress at a point. Sir, what is the meaning of stress at a point? Please remember, the stress is always defined at a point only. But generally, the students understand the stress term is related to the plane. It is not related to the plane. It is always defined at a point only. Don't think like that. The stress is okay, same throughout the plane here. It is not same throughout the plane. The stress values varies from point to the point. Okay. Suppose, for example, if you look at the bending stress, okay, if you look at the bending stress diagram also, the bending stress is 0 at the neutral axis. It is maximum at outermost layer. Suppose we can think it is same throughout the plane here. Okay, then the bending stress also should be same throughout the plane. But is it the same throughout the plane? No. The bending stress is 0 at a neutral axis. That value is goes on increases. It is maximum at outermost layers. That values goes on increases. Okay, from that diagram, what we should understand? Okay, it is defined at a point only. That's why, okay, I am calling as a stress at a point. I am considering this cuboid is a point. Okay, cuboid is a point is a three-dimensional. Okay, for three-dimensional structure, to define the stress at a point, okay, 9 stress components are required. Out of 9 here, 3 normal stresses and 6 shear stresses. Due to the complementary shear, okay, tau ij is equal to tau ji, that means tau xy is equal to tau yx here. Like that, no need to calculate the 6 shear stresses here, just we can calculate the 3 shear stresses. The remaining 3 are equal to these 3 here. So to define the stress at a point, okay, independent stress components are 6. Okay, this is the 3-dimensional. Okay, and also this is this matrix we are calling as a stress tensor matrix here. The matrix representation to define the stress at a point is called as a stress tensor. Okay, and next one. Don't think like that. Always we can design the 3-dimensional member. Sometimes we can design the 2-dimensional member also. Okay, while designing the 2-dimensional member, okay, we can neglect the one plane here or one direction. We can neglect the one direction. Suppose, for example, we can neglect the z direction. That means there is no stress in the z direction. Then this 9 stress components, now it becomes only 4 components here. What are those 4 components? One is the sigma xx, and the second one is the tau xy, third one is the tau yx, and fourth one is the sigma yy. This remaining, we can look at the remaining 5 components here which are related to the z. That's why those values are 0. That means only 4. Okay, 2 normal stresses and 2 shear stresses here. But we may get a one doubt here. Sir, have you seen any 2-dimensional bodies? Yes, so many places we can look at the 2-dimensional bodies here. Suppose, for example, thin pressure vessels. Okay, thin pressure vessels are there to store the fluid here. It is in the thin pressure vessel, the thickness is very, very small. We can neglect the thickness here. Only we are considering the 2 dimensions here. One is the length, second one is the diameter. The third direction thickness, we can neglect the thickness here. Okay, we can consider those 2 directions only. For those thin pressure vessels, okay, we can considering this stress distribution here. That means we can calculate these 4 here. The 4, not a 4 here, we can calculate the 3 only. Okay, 2 normal stresses, 1 shear, because okay, because of complementary shear, tau xy is equal to tau yx. Okay, that's why we can look at the thin pressure vessel. We can calculate the longitudinal stress. Okay, I think sigma L is equal to PD divided by 4T here, and circumferential stress here PD divided by 2T here, and maximum shear stress here PD divided by 8T. Okay, that longitudinal and the circumferential stresses both are called as a normal stresses. So we can assume that one is the sigma xx, another one is the sigma yy here, and the next one is the maximum shear stress PD divided by 8T here. Okay, that value we are considering as a tau xy. Okay, that's why for 2-dimensional, no need to calculate the 9 components. We can calculate the 4. Sorry, actually 3. Independent is 3. Generally, we can calculate the 4 here. But we may get a one doubt. Sir, it is a 1-dimensional. We can calculate any one only. Okay, we can calculate the normal stress or we can calculate the shear stress here. Okay, but one thing you remember, normal stress means what I said, the stress which are induced perpendicular to the direction of the plane is called as a normal. Okay, ultimately the normal stress further classified into the 2 types here. One is the tensile stress and the second one is the compressive stress. Okay, that stress is away from the member, it is called as a tensile. Towards the member, it is called as a compressive. Okay. Ultimately, we can observe here tensile stress, compressive stress, and shear stress. That tensile stress should be less than the tensile strength of the material. The shear stress should be less than the shear strength. Compressive stress should be less than the compressive strength of the material. Then the member is safe. Otherwise, the member is failure. Okay. This is two-dimensional state of stress here. And now, the next one is the types of loads acting on the member. You can look at the first figure. The member is subjected to compressive load. Okay, that means the load is acting towards the member. And the second one, you can look at the second figure. Okay, the member is subjected to the tension. That means the load is acting away from the member here. Third one is a shear. Shear means the force which is acting okay on the plane, parallel to the plane, tangential to the plane. It is called as a shear. Okay, this kind of shear forces acting on the beams. Okay, due to the transverse load, the beam is subjected to the shear force. Okay, the next one is the torsion. The shaft is always subjected to the twisting moment here. Okay, now there is a two kinds of the moments. One is the twisting moment, second one is the bending moment. The shafts are always subject to the twisting moments, and beams are always subjected to the bending moments here. Next one is the bending, means like this here. Okay, the beam is supported by the two or more than two supports here. Okay, the load is transverse load is acting here. Due to that one, the bending stress will be developed here due to the bending moment. These are the loads acting on the member. Now, okay, one thing you remember, the first one, compression and tension is there. Okay, the member which is subjected to the tensile load or compressive load, then that member is called as a bar. Okay, to calculate the stress, we are using the sigma is equal to P by A. Okay, and the next one is the torsion. We can look at the next one, torsion. Okay, in this torsion, the member is subjected to the twisting moment. The member which is subject to the twisting moment, it is called as a shaft here. And we can look at the shear or bending, both are there. Okay, in these cases here, the member is subject to the bending and shear, then that is called as a beam. Okay, so first we have to identify, because okay, suppose for example I want to calculate the how much deformation will be developed in the bar. Yes, we have the one formula, delta is equal to PL by AE. Okay, if you want to calculate the deformation in the shaft here, we are using the formula theta is equal to TL divided by G there. That's why first we have to identify the member, not only the deformation. To calculate the stress, to calculate the strain energy, first we have to identify the member. The stress equations are different for different members. The deformation equations are different for different members. The strain energy equations are different for different members here. Okay, could you understand the students? Hello?
Yes, sir.
Hello?
Sir.
Could you understand?
Sir.
Hello?
Yes, sir.
Okay.
Understand, sir.
Yes, sir.
Okay. Next one, types of stresses. Yes. Already I told that the stresses are mainly classified into the two types here. One is the normal stress, which are developed perpendicular or normal to the plane, which is represented by the sigma here. Second one is the shear stress here. Okay, what I said here, the stresses which are developed parallel or tangential to the plane, it is called as a shear stress here, which is represented by the tau. The normal stress further classified into the two types here. One is the tensile stress, second one is the compressive stress. Already I told that this is the classifications of the stresses. There is no further classifications in the shear stress. There is no further classifications in the shear stress here. Okay, ultimately we can look at here, there is a three stresses. One is the tensile stress, second one is the compressive stress, third one is the shear stress here. Okay, the stresses are three ultimately. The strength also three here, tensile strength, compressive strength and shear strength. Okay, now if the compressive stress will be developed in the member, that value compare with the compressive strength of the material. Shear stress developed in the member, that value compare with the shear strength of the material. Okay, tensile stress will be developed in the member, that value compare with the shear strength of the material. These the values, the stress values always less than the strength of the material, then the member is safe, otherwise it is failure here. Otherwise it is failure here. Next one. Fracture from the three types of the stresses here. Okay, suppose for example, okay, if you are applying the tensile load on the member, Suppose for example, every material has some internal resisting force. Already I told that. Suppose for example, you can look at the first member. It has the 70 kilonewtons internal resisting force is there. That is the maximum capacity of the member is 70 kilonewtons. If you are applying the more than 70 kilonewtons load on the member gets failure and it is fractured. Okay, now we can look at the figure how it can fracture in the tension. And the second one, compression. Okay, that means suppose for example, this member is a ductile material. If you are applying the small amount of compressive load, it can break it. Suppose it is a brittle material. Okay, that means it can carry the maximum compressive loads. Maximum compressive loads here. Previously, I told that. Okay, ductile materials are very strong in the tension. Brittle materials are very strong in the compression. Okay, that's why what I said, while designing the member, okay, first we can select the material, what kind of material we can use for a particular member. That is depends upon the loads, what kind of loads are acting on the member. Okay, the tensile loads are acting on the member, please select the ductile material. Compressive loads are acting on the member, please select the brittle material here. Okay, like that. And the third failure is shear failure. Okay, now we can observe here the shear failure is you are applying the forces like this here, parallel to the parallel forces like this. The member gets sliding. That is called as a slip. It is called as a shear. Next one. This is the very beautiful sentence. Okay, sir, how to identify whether it is the normal failure or shear failure? First two are normal failure, second one is a shear failure. Suppose we can apply the loads directly, we can identify, but sometimes we are applying the load somewhere, but the stresses will be developed at the somewhere here. In such a case, it is very difficult to identify what kind of failure it will occurs in the member. Okay, very simple. The normal failure means the direction of the normal failure is always normal to the direction of load. Direction of the normal failure, we can look at the direction of the normal failure is always normal to the direction of the load. The failure direction is horizontally. We can look at this figure. The failure is occurs horizontally, but we are applying the load vertically. In the compression also like this here, the failure occurs horizontally, we are applying the load vertically. But whereas in the shear is not like that. We are applying the forces horizontally, but the failure also occurs in horizontal direction. The direction of the failure normal to the direction of the load is called as a normal failure. The direction of the failure is parallel to the direction of the load is called as a shear failure. Okay. Could you understand the students? Hello.
Yes, sir.
Hello.
Yes, sir.
Could you understand how to identify the types of the failure, normal failure and shear failure? Hello.
Yes, sir.
Yes, sir.
Okay.
Sir, myself,
Okay.
sir.
The direction of the failure is.
Sir,
Sir.
Sorry for the interruption, sir. The class is only for sir. We are scheduled classes for
Hello.
only for 1 hour, sir. I hope
Sir, okay.
up to 4, sir. Sorry.
Sir, 1 minute, sir. We can look at sir, no problem, sir. Stress is.
Okay, sir.
Sir, this is up to stress only.
Okay, sir.
Sir, is there any other class?
No, sir.
Sir, we have any other class? Sir, Sunny, sir? Hello? Hello? Sir, okay, sir. Can I stop? Hello? Hello?
Sir, 5 o'clock other class, sir.
Oh, at 5 o'clock we have another class.
Yes, sir.
Okay, no problem. Last sentence. The direction of the failure is perpendicular to the direction of the load is called as a normal failure. Parallel to the direction of the load is called as a shear failure. Can you conclude the today's class? Just 5 minutes. Hello?
Okay, sir.
Sir,
Yes, sir.
can you conclude
Yes, sir.
the total 1 hour class in just 5 minutes?
Okay,
Because it
sir.
is a very, very important
Yes, sir.
class here. We can't understand, sometimes. Please remember, in the strength of the material, not only the strength of the material, if it is a civil students, to design any member in the structure, SA or RCC, or mechanical students and machine design, Okay, these subjects are, we can look at here, these all subjects, okay, the main intention of these all subjects is to design the member. Okay, we can design the member without failure. That is our intention. Okay, please remember, to design the any member, member means bar, it is a one kind of member. Beam, it is another kind of member. Shaft, it is another kind of member. Frame, okay, truss, okay, column, these are the different kinds of the members. To design the any member, we have to consider in the four criteria here: strength criteria, stiffness criteria, stability criteria, and strain energy criteria. And strain energy criteria here. Okay, these four criteria are very important here. The strength criteria says that the stress is less than the strength of the material, then it is safe. The stress is found by doing the experiments here, and the strength is found by doing the experiments here. The stress can be calculated by using the equations here. We are using a different equations for different members. Okay, and the next one is the stiffness criteria. Okay, we can calculate the deformation. Deformation produced due to the external load is always less than the permissible deformation. The member gets the member, it permits the some amount of deformation. That value is always more than the deformation induced due to the external load, then it is safe, otherwise failure. Like a strain energy also like this here. And stability, please remember, okay, the stability, the member should be in stable condition. When it is in the stable condition, the center of gravity is nearer to the ground, then it is in the stable condition, otherwise it is in the unstable condition. Okay, this is the first one here. That is the types of criteria we are going to consider here. The next one, the stress. The stress means internal resisting force per unit area. Don't call as a load per unit area. But while doing the problems, we are calling as a load per unit area here, because when the member is designed up to elastic limit only. Okay, without internal resisting forces, there is no stresses here. The internal resisting forces cannot be developed. Okay, then due to the external load, work done will be developed here. There is no stresses will be developed here. And okay, stress at a point, the stress is defined at a point, not defined at a plane here. Just we can observe the bending stress distribution diagram. Okay, the bending stress distribution diagram, shear stress distribution diagram, you can look at these diagrams here. We can understand very easily the stresses varies on a plane at each and every point. That's why, okay, stress at a point, okay, for 3-dimensional, there is a 9 stress components are required, 3 normal and 6 shear here. It is a tensor quantity here. Okay. And the next one, okay, in a 2-dimensional, there is a 4 stress components are required here. Okay, out of 4 shear stress tau xy is equal to tau xy. That means 1 stress shear stress and 2 normal stresses here. That is the 2-dimensional member. And types of loads already explained here. Next one, types of the stresses. Ultimately, one thing you remember, we can take the any stress. Okay, it may be the tensile or compressive or shear only. Ultimately, these three. Okay, suppose for example, we can calculate the normal stress. Okay, 50 megapascals. Is there any normal strength here? There is no normal strength. Only tensile, compressive and shear. Okay, 3 kinds of the strength. That's why there is no normal stress. That's why you can calculate the compressive stress or tensile stress or shear stress. Okay, only these 3 only. The tensile stress compare with the tensile strength of the material, and compressive stress compare with the compressive strength, and shear stress compare with the shear strength of the material. Okay, this is about the stress here, and next class we will discuss about strain. Okay, thank you very much. Hello.
Thank you, sir.
Thank you.
Thank you.
Okay, sir. Thank you very much.
Thank you very much.
Okay, sir. Right.